Already we have seen in this one uh, some related questions. So your null hypothesis is P is less than or equal to 0.5, that is probability, while your alternate hypothesis is P is greater than 0.5, where P is the probability that the coins source of a head. Say now you want to perform your hypothesis testing at a 10% level of significance. What you do now is to do as follows. Let NH, N capital H be the number of hits observed out of total of N doses of the coin. Take a P equal to 0.5, probability equal to 0.5. The extreme case of the null hypothesis. Let X approximately equal to B n comma 0.5, 0.5. Let X similarity B of n comma 0.5. Let's say X similarity. It is the not in size, it is the same shape. P P of X is greater than or equal to NCH equal to 0.1. NCH gives you the critical value beyond which you have sufficient evidence to reject the null hypothesis at 10% level of significance. That is, if you find NH is greater than NCH, then you have sufficient evidence to reject the null hypothesis at a 10% level of significance and conclude that the coins comes up heads more often than tails. If you want to determine if the coin is unbiased, if you need to do a two-sided hypothesis testing as follows. Your null hypothesis is P equal to 0.5, while your alternate hypothesis is P equal to percentage 0.5, where P is the probability that the coin shows up a head. Say now you want to perform your hypothesis testing at a 10% level of significance. What you do now is to do as follows. Let NH be the number of heads observed out of a total number of N doses of the coin. Let X similarity P of N comma 0.5 compute NC1H and NCH2 as follows. P of X less than or equal to NC1H plus P of X greater than or equal to NC2H equal to 0.1. NC1H and NC2H are symmetric about N2, that is NC1H plus NC2H equal to N. NC1H gives you the left critical value and NC2H gives you the right critical value. If you find NH, NC1H and NC2H, then you have to not have sufficient evidence against a null hypothesis and hence you accept the null hypothesis at a 10% level of significance. Hence you accept that the coin is fair at a 10% level of significance. Why we cannot use linear regression for a dependent variable with binary outcomes? The linear regression can produce predictions that are not binary and hence nonsense in interactions that are not accounted for in the regression and non-linear relationships between a predictor and the outcome. Inference based on the linear regression coefficients will be incorrect. The problem with a binary dependent variable is that the homo, homo, homoscedasticity assumption similar variations on the dependent variable for units with the different values on the independent variable is not satisfied. I will add the another concern is that the normality assumption is violated. The residual from a regression model on a binary outcome will not look very well shaped. Again, with a sufficient large sample, the distribution does not make much difference since the standard errors are so small anyway. How to estimating sample size required for experiment? How to estimating sample size required for experiment? Sample sizes may be chosen in several different ways. Experience for so example include those items readily available or convenient to collect. A choice of small sample sizes, though sometimes necessary, can result in wide confidence intervals or risk of errors in statistical hypothesis testing. Using a target variance for an estimate to be derived from the sample eventually obtained. Using target for the power of statistical testing to be applied once the sample is collected. How to determine the sample size? For a study for which goal is to get a significant result from the test. How to determine sample test? For a study for which the goal is to get a significant result from a test. Set alpha to the residual power. Set HA estimate sigma. For example, simple linear regression model. Deterministic relationship is one in which the value of y is completely determined by the value of independent variable x. Such a relationship can be described using traditional mathematical notation such as y equal to f of x, where f of x is a specified function of x. For example, we might have y equal to f of x equal to 10 plus 2x, or y equal to f of x equal to 4 minus 10 power 2x. However, in most situations, the variables in interest um, the variables of interest are not deterministically related. For example, the value of y equal to first year college grade point average in a certain not determined solved by x equal to high school grade point average, and y crop equal to crop yield is determined partially by factors other than x equal to amount of fertilizer used. A description of the relation between two variables x and y are not deterministically related can be given by specifying a parallelistic model. The general form of additive probabilistic model allows y to be larger or smaller than f of x by a random amount e. The model equation form the model equation of the form y equal to deterministic function of x plus the model equation of the form y equal to deterministic function of x plus random deviation f of x plus e, that x denote some particular value of x, and suppose that an observation on y is made when x equal to x, then here, here okay, y is greater than f of x. If e equal to e is greater than 0, y is less than f of x. If e less than 0, y equal to f of x. If e equal to 0, thinking geometrically, if e is greater than 0, observed point x comma y will lie above the graph of y equal to f of x. E is less than 0 implies that this point will fall below the graph. This is illustrated in figure 13.1. If f of x is function used in a probabilistic model relating y to x, and if observations on y are made for various values of x, the resulting x comma y points will be distributed about the graph of f of x, some falling above it and some falling below it. The deviation from the deterministic part of a probabilistic model in exercise. Therefore, graph of this is y equal to, sorry, like this, y equal to 50 minus 10x plus x square. Observation here 26, here 40, observation 4 comma 30, 4, 30, but here 4, 26 minus 30, deviation from deterministic part of probabilistic model. The simple linear regression model is a special case of general probabilistic model in which deterministic function f of x is linear, so its graph is straight line. Here, the simplest regression model assumes that there is a line with a vertical or y-intercept alpha and slope. We called the true or population regression line when a value of the independent variable x is fixed and an observation on the dependent variable y is made. Y equal to alpha plus beta x plus e without the random deviation. E all observed x comma y points will all exactly on the population regression line. The inclusion of E in the model equation recognizes that points will deviate from the line by random amount. The figure shows several observations in relation to the population regression line. Several observations resulting from the simple linear regression model. Several observations resulting from the simple linear regression model. In the x-axis, here x equal to x1, here x equal to x2. Here alpha vertical intercept observation when x equal to x of 1 positive deviation,